Today we are going to start the next topics, that is integer programming, integer linear programming problem. If you see, till now we were solving problems something like this: maximize z equals c x, subject to a x equals b, and your x, that means you can write down x j belongs to x is greater than equals 0. We were solving this kind of problems: maximize z equals c x subject to a x equals b, where x j all variables are greater than equals 0. So, the variables can take the integer value, can take the real value, they have to be positive. But if you see, in real life there may have several examples where the variables can take only integer values. You just take one example, say a the company produces two different type of shirts or three different type of shirts. Whenever they are producing the shirts, they are using the tailors. So, the tailors can produce say 5 shirts in 7 hours of type 1, and one tailor can produce, the other tailor can produce say 10 shirts in 5 hours, something like that way. The profit per shirt is known to the management of the company. So, therefore, whenever I want to optimize the function, that is how many types of say type 1 shirt and how many types of type 2 shirts should be produced by the tailors, so that the profit of the company will be maximized. In this case, the decision variables will be the number of shirts produced for type 1 and number of shirts produced for type 2. Let these be our x 1 and x 2. So, whenever you want to find out the solution always must be integers, because you are producing number of shirts. So, in this case x 1 and x 2, the variables cannot take the real number or real values. So, like this several examples can be given where the values of the decision variables will be positive and integer only, it cannot take real values. So, if I am facing a problem, say I am adding one more constraint on this and x j are integers. So, I am writing x j greater than 0 and x j are integers. If my problem is this one, that maximized z equals c x subject to a x equals b and x j greater than equals 0 and x j are integers. So, if I have a problem, this type of problems are known as integer linear programming problem, where we are interested to find out the maximum value of z, where the variables x j can take only integer values. So, if I have some problem where the variables can take only the integer values, we call that type of problems as pure integer problem, where the values, the decision variables can take only the integer values. Whereas, if the decision variables can take both real and integer values, that is some variables can take any type of value, any positive value, whereas some variables can take only integer values. This kind of problems are known as the mixed integer programming problem. So, in this particular lecture we want to see how to solve this kind of problems. Basically, if you see, we are having two different type of, we will discuss two different type of approaches. One is Gomori's cutting plane method and another one is branch and bound method. The Gomori's cutting plane method, the first one, Gomori's cutting plane method. This method was developed by R. E. Gomori. Basically, what he has done, he has introduced a new constraint in this particular problem. By addition of the new constraint, what it does is tries to remove the non-integer optimal variables. That means, the variables which are in the basis, and if the values are non-integer, by introducing the new constraint is tries to remove those kind of variables, but the feasible variables or the optimal variables which are in the basis, but whose values are integers, those are remain unaffected. That is, if the value of a variable which is present in the basis and whose value is integer, that variable will not be affected. So, the basic criteria or basic idea is to add a new constraint on this particular this. That means, what it does, you are having the original problem, you are solving the original problem by the normal method, whatever you have done by the usual simplex method, and you are obtaining some optimal solution. Once you have obtained the optimal solution, means z j minus c j is greater than equals 0 and the values of the basic variables are known to you. Please check whether the values of the decision variables are all integers or not. If the values of the decision variables which are present in the basis are integer, then you can stop. But if it is not integer, then introduce a new constraint which we call as Grammarians cart. Please note, which we call as Grammarians cart, and using this Grammarian cart we modify the earlier problem and then we try to resolve the problem. This is the basic idea of this Grammarians cutting plane method. Let us see how we can perform this job. Let us have the following table. I am just writing the following table here. You are having C B, B, X B, B, some variables y 1, y 2 like this way, y k, you are having y m. I am just dividing. Here you are having y m plus 1 into y n, that is basically you are having the n decision variables. Here you can incorporate some cost associated with it, and you are having this is C j, already you have done z j, this is z j minus C j. So, these values are C 1, C 2, C k and C m say, and these values similarly may be C m plus 1 to C n. Here you are having y 1, y 2, y m in the basis. So, you are having x 1, x 2 like this way, x m. Your b values are b 1, b 2 like this way, b m. So, C 1, C 2 you are having say C k here and C m. This for convenience actually I have written it as identity. If you see 0, 0, 0, this is 1. Here some values are associated y 1 m plus n, y 1 n. Similarly, the last line I am writing, that is y m m plus 1 and y m n. These values have been becoming 0, but they have some values say z m plus 1 to z n. So, here if you see x 1, x 2, x m, these x 1, x 2, x m are the basic variables, and remaining n minus 1 variables, that is x m plus 1 to x n, these are non-basic variable. Now, suppose the kth basic variable corresponds to some non-integer value in the optimal solution. This kth basic variable, that is y k and x k, this and this b k. So, kth basic variable is corresponds to some non-integer value. That means, you can write down this kth basic variable or x b k like this way. X b k, this is equals, you can write down 0 into x 1, just I am writing the row, 0 into x 2 plus 1 into x k, kth basic variable is non-integer, plus 0 into x m plus your y k m plus 1 into x m plus 1, like this way you are going as plus y k n into x n. So, from this y b k you are writing this one 0 0 1, this is 0 and some values are over here. So, from this kth basic variable I am writing x b k in this form, x k is present. So, this actually x k plus summation over L equals m plus 1 to n y k l into x l, you can write down, and from here you can write it x k, this x k is on this side equals x b k minus the summation from what I was telling L equals m plus 1 to n into y k L into x L. So, it is equation 1. Now, your x b k, this is non-integer. So, you can write down, since it is non-integer, x b k I can write as I b k plus f b k, and correspondingly y k L also I can write down I k L plus f k L, where I b k and I k L are the integers part of x b k and y k L, and f b k and f k L are the fractional part of x b k and y k L respectively. Since both are non-integer, so there will be one integer part, one will be fractional part. So, we are assuming I is the integer part and f is the fractional part, or in other sense your f b k, if you say your f b k and f k L both basically belongs to this value, close bracket 0 and open bracket 1. These are the fractional parts. So, from 1 you can write down x k equals I b k plus f b k minus summation L equals m plus 1 to n x L into I k L plus f of k L. So, if you break it, we can write down this as f b k equals f b k minus summation over L equals m plus 1 to n x L into f k L. This is equals x k minus I b k minus summation over L equals m plus 1 to n x L into I k L. Now, look at this right hand side. Right hand side contains your x k, your I b k, x L and I L it and I k L. This should be integers, or in other sense the right hand side should be integer. Therefore, the left hand side, that is f b k minus summation L equals m plus 1 to n x L into f k L, this also must be integer. And please note that f b k lies in between 0 to 1, and your, so from these two you can write down f b k minus summation over L equals m plus 1 to n x L into f k L, this is f k L, this should be less than equals 0, since it is an, this is an integer value. So, it should be either 0 or it should be a negative number. So, you are getting this above inequality. This above inequality can be made equality constant using one slack variable, which we call as Grammarian slack variable, and we can make it as equality constant, that is f b k minus summation over L equals m plus 1 to n x L into f k L plus g k equals 0. This, so where this g k, this we call as the Grammarian slack variable. So, for it should be integer, what basically we derived? We derived that for integer what should be the condition? The condition is this should be less than equals 0 for a particular Lth kth variable. So, we are introducing one slack variable which we are calling as Grammarian slack variable, and we are writing this. So, this you can write down minus f b k, that is we in general f b k should come on the left hand side, minus f b k equals minus summation over L equals m plus 1 to n x L into f k L plus g k. This, that means f b k you are just taking on the other side, and this equality constant 3 is known as Grammarian cut, or we call it as Grammarian cutting plane. So, If you see the non-basic variable XL, L can take any value m plus 1 to n, and since your GK is minus FBK, therefore, always it will be infeasible. So, basically B value will be negative, or in other sense FBK is nothing but the B value. So, B value will be negative, means the variable kth variable will be going or will be entering into basis. Since it is negative variable, therefore, you can use the dual simplex method to solve the problem. So, basic idea is whenever you are having fractional value, you choose a particular variable. How to choose the variable, that I will tell just after this, and you introduce the Grammarian cut and introduce Grammarian slack variable and find out an equality constraint like equation 3. From this equation, FBK minus summation L equals m plus 1 to n XL FKL, this is less than equals 0. So, you can see this thing. Let us see the flow chart for this one. If you see the flow chart, I will just come to it. We are starting from this problem. Reformulate the given IPP in the standard form. That is, already you know how to write the LPP in standard form. So, we are telling reformulate the given IPP in the standard form. Ignore integer restriction and solve IPP as usual by simplex method. That is, forget about whether the decision variable takes the integer value or real value, just forget it and find out the solution of the problem by using the simplex method, whatever we have done. So, once you obtain the simplex by simplex method the solution, now check this one. The next step is this one, that is, does this optimal basic feasible solution satisfy integer constraints, or in other sense the decision variables or the variables which are in basis, whether the values of them are integer or not, that we are checking here. If all the values of the basic variables are integer, then current basic solution is the integer optimal solution, and you stop over here. If it is no, you see this branch, if it is no, then find the basic variables having the largest fractional part. That means, you may have more than one basic variable which is having the largest fractional part. Now, from the largest fractional part, what you do? You choose that variable which has the largest fractional part. Okay. So, how to choose which variable for which you will use Grammarian cut? The mechanism is find out the variable which has the largest fractional part. If there is a tie, you can choose any one of the variables. So, once you have chosen the largest fractional part and corresponding basic variable, then you write the corresponding constraint equation for this variable. You write the corresponding constraint equation for this variable, find the Grammarian slack variable and Grammarian cut for this variable. Or in other sense, you are just what I was telling, you use this one, that is, you form an equation for that variable of the type of equation 3 what I have discussed. Now, once you have done this new constraint will be added to the last simplex table what you have done. That is, suppose there was 3 variables in the basis, in that case after introducing the new constant 3, there will be 4 variables, the fourth variable will be the xk which has having the largest fractional part, and you fill up the table with this row of the 3. Minus FBK means B value, and you are taking, please note one thing, here we are taking for L equals m plus 1 to n XL FKL. That means, for the variables for that row you will take only those where you are having the fractional part. So, once I have done this, then modify the simplex table for optimal non-integer solution by adding one more row and use dual simplex method. As I told you, you add equation 3 as one row and use, because the value will be negative. So, use dual simplex method after that to find out the solution, and Grammarian slack variable will be the initial leaving vector, automatically it will come because that will have the largest negative value. And so, Then again you test the feasibility. If the optimal basic feasible solution gives you all the values of the variables as integers, then you stop or repeat this process. So, this is the flow chart of solving a problem using Grammarian cut method. Now, let us see, take a problem, let us take one problem, maximize z equals x 1 plus 3 x 2 subject to 3 x 1 plus 6 x 2 less than equals 8, 5 x 1 plus 2 x 2 less than equals 10, x 1 and x 2 greater than 0, greater than equals 0 and are positive integers. So, we have added this, both x 1 and x 2 are positive integers only. So, as per our flow chart, if you see, reformulate the given LPP in IPP in the standard form. So, in standard form means I have to make it equality. So, introduce two slack variables. So, maximize z equals x 1 plus 3 x 2 plus say 0 into x 3 plus 0 into x 4 subject to 3 x 1 plus 6 x 2 plus x 3 equals 8 and 5 x 1 plus 2 x 2 plus x 4, this is equals 10, and the condition of x 1, x 2, x 3, x 4 will remain the same. So, from here you formulate the first simplex table. From here you formulate the first simplex table the way we did earlier, that is, if you see, for this problem your entering variable will be x 3 and x 4 because they are forming the identity matrix. So, therefore, in B basically you will have y 3 and y 4 and your x b is x 3 and x 4, y 1, y 2, y 3 values are 1, 3, 0 and 0. So, I am writing 1, 3, 0 and 0. So, C b value will be corresponding to y 3 and y 4, it is 0 and this is also 0. Now, write down the first row over here, b value is 8, then 3, 6, 1, 0, these are the coefficients. If you see here 3, 6, 1 and x 4 is 0. So, write down 3, 6, 1 and 0. The next one is b value is 10. So, write down b value as 10 over here, and this one is 5, 2, 0 and 1 coefficients of x 1, x 2, x 3 and x 4. So, this is 5, 2, 0 and 1. Already we have done these things. So, now find out the zj minus cj values. So, cb into yj minus cj. So, I am just directly I am writing the values, this is minus 1, the next one is 0 is there, minus 3, next one is 0, next one is 0. So, therefore, most negative. So, as you know, this is minus 3, this is the entering vector. So, it is 8 by 6, whereas this is 10 by 2, minimum of these two is this. Therefore, x 2 will enter and x 3 will be leaving the basis, and this is your pivot element. I think it is clear, already we are doing this. So, from here now we have to make this value of this one pivot element as 0 and in the subsequent row this value as 0, the necessary operations. So, I am just writing first the entering vector will be y 2 and y 4, because your x 3 is leaving and x 2 is entering. So, x 2 and x 4 will come over here. Your value of C j is 1 3 0 0. So, we are writing 1 3 0 0. So, C b will be your 3 and 0, your C b is 3 and 0. So, basically you have to make this as element as 1 and this element as 0. So, first row you are dividing by 6 and for the second row you are multiplying by 3 second row and then subtracting. So, I am writing the result, the value is like this 4 by 3 half 1 1 by 6 and 0. This variable was 1, correspondingly you will get 22 by 3, 4, 0, minus 1/3 and 1. So, now find out the Zj minus Cj values. So, 3 by 2 minus 1 half, 3 minus 3 0, then half minus 0. So, it is half and the next value is also 0 0 minus 0. So, it will be 0. So, here if you see Zj minus Cj is greater than equals 0 for all j, and Zj minus Cj is greater than 0 for non-basic variables y1 and y3. y1 and y3 are non-basic variables. So, for y1 and y3 non-basic variables, therefore, as you know, you are obtaining the unique optimal solution. What is the optimal solution? Optimal solution is x1 star equals 0, x2 star this is equals 4 by 3 and your z star you can calculate from here what would be the value of z star. I am not writing, the equation was 1 3. So, basically your the value was x 1 plus 3 x 2, that was z. So, therefore, z star is 4. But if you see here, although we obtain the optimal solution, but one decision variable has the non-integer value, this x 2 is 4 by 3. Therefore, but we wanted that x 1 and x 2 should be integers only for both cases. So, therefore, we cannot take this as the optimal solution. So, now what I have to do from here? I have to use the Grammarians method to solve the LPP. What we have told? The here fractional part of x bi is which one? Fractional part are 2, 4 by 3 and 22 by 3. And so, you have two non-integer variables, one is 4 by 3, another one is 22 by 3. Therefore, for both cases the fractional value is 1/3 only, this is 1/3, 7 into 1/3. So, for both cases the fractional value is 1/3. So, therefore, you can take any one of these two variables x 2 and x 4, because there is no largest element which has the largest variable, the variable which has largest fractional part, the fractional part of both are same in this case. So, for this what I have to do? My formula is, if you remember, x b k minus summation L equals m plus 1 to n f of x l into f of k l into x l less than equals 0, where f b k is the fractional part of 0. So, what is your f 0? We are taking the variable x 2. So, what will be the value of first f 10? F 10 means the basically the b value. F 10 means fractional part of this b value, that is 1/3. So, we are writing f 10 equals 1/3. Now, on this row how many fractional values are there? Fractional values are coming, one in y 1, another in y 3. If you see here, we will take only those L's, L equals m plus 1 to n, where you are having fractional values. If you have integer values, we will not take those. So, basically we will not take y 2 and y 4, we will take y 1 and y 3. So, f 11, that is the coefficient corresponding to y 1, this is equals to half. So, I am writing half 1 here. F 12 will not come because it is 0, again f 13 is 1 by 6 here. So, f 13 this is equals 1, this is equals 1 by 6, and f 14 again is 0. So, that will not come into picture. So, therefore, you are writing your f 10, that is the b value from this corresponds to this table. We have considered the variable x 2, both are having equal fractional part. So, we have taken x 2. For b value fractional part is 1/3. So, you have taken f 10 1/3. The next one is corresponding to y 1, I have fractional value. So, I am writing f 11 equals half, and then again you see corresponding to y 3 you have having fractional value 1 by 6. So, you are writing f 1/3 equals 1 by 6. Now, if you substitute in this, so basically your equation I am writing this, afterwards I will write down directly f 11 x 1 plus f 13 x 3, this is less than equals 0. So, now put the values, already I have written the values, minus half x 1 minus 1 by 6 x 3 less than equals 0. Now, introduce the Grammarian slack variable or the Grammarian cut, and you can write it as minus x 1 by 2 minus x 3 by 6 plus s 1 equals minus 1/3, that is going on that side. So, where your s 1 is the Grammarian slack variable. So, basically now what happened, you got one more constraint over here, or one more. Now, there was one more inequality constraint. Using Grammarian slack variable, you have incorporated the, you have made it equality constant, and therefore, you got another equality constant. This was your last table, if you remember, where you got the optimal solution, right. So, with this I have to add one more variable, that is here your one more variable, that is S 1 I have to add, slack variable is S 1. So, S 1 will come enter into basis, and corresponding to S 1 this row I have to add, this row I have to add in this table. So, therefore, if you see in the next table, you are having, you was having already y 2, you are having y 4, and one more variable is coming S 1, and here you are having x 2, x 4 and S 1. So, if you see in the last optimal table, you had two basic variables x 2 and x 4. Now, you have added one more equality constant using the slack Grammarian slack variable S 1, what I have shown over here, and this row will come over here, and all other rows, that means this entire thing will remain the same. So, I am just copying from here, the values will be 1, 3, 0, 0, 0. So, y 2 means 3, y 4 is 0, S 1 is not in the objective function, again 0. So, I am just writing this coefficient again, if you see 4/3 half 1 1 by 6 0, directly we are writing whatever was there 4/3 half 1 1 by 6 and 0. The next variables, the next row same 22 by 3 4 0 minus 1/3 and 1. So, again you are writing this 22 by 3 4 0 minus 1/3 and 1. So, these two row remains intact, you have not changed this. Here your S 1 value is 0, here also S 1 value is 0. For the first two variables S 1, equality constants S 1 was not there. So, we are making the coefficient of S 1 as 0 over here. So, we are doing this thing. Now, once you are getting this, now for S 1 what will be the row? This row will be the coefficients with respect to this. B value will be minus 1/3, this minus 1/3. So, I am writing over here minus 1/3. Coefficient of x 1 is minus half, x 2 is 0, x 3 is minus 1 by 6, S 1 is 1. So, basically it will be minus half, 0, minus 1 by 6, 0 and 1. So, I am writing that minus half, 0, minus 1 by 6, 0 and 1. So, I feel it is clear now. You are having the last optimal table up to this, then you have added one more Grammarian constant, and that row you are adding as this S 1 is entering over here. And if you see why we told S 1 will have S 1, if you remember, the Grammarian cart variable will be leaving variable, because here the b value is negative, it is always negative. Let us calculate the zj minus cj value. Zj minus cj value is 3 by 2 minus 1. So, it is half. The next one 3 minus 3 0, then it is half. Next one 3 into 0, other two are 0. So, 0, 3 into 0, this is 0. So, now you see Zj minus Cj is greater than equals 0 for all j. Zj minus Cj is greater than equals 0 for all j, but the solution is infeasible, because the value of one basic variable is negative. Value of one basic variable is negative, therefore, the solution is infeasible. So, what we will do? If I have a negative value, we will not use the normal simplex method, we will use now dual simplex method to solve the problem. In dual simplex method, first what would be the outgoing vector I have to check the outgoing vector. Basically, we calculate maximum of Zj minus Cj by Yj, negative of Yj, where Yj is less than 0. That is, I am just writing, just reminding you, 1 will be half by minus half, because here only you are having negative value, and here this is half by minus 1 by 6. So, obviously, the first one is having the maximum value, that is minus 1, which corresponds to this one, therefore, this one is the outgoing. And on this column you are having only one negative value, I am not discussing, because already in dual simplex we have discussed. So, your entering vector now will become this minus half. So, you are writing minus half over here, and this is the your pivot element. So, in the next table your S1 will be departing and X1 will enter. So, your it will be Y2, Y4 and Y1. Here you are having X2, X4 and X1. Cj values are same 1, 3, 0, 0, 0. So, therefore, your Cv values will be 3, 0 and Yx1 is 1. So, coefficient is 1. So, basically I have to make this variable as 1 and corresponding rows, columns, these values as 0. Directly I am writing the result, because you know how to do it. 1, 0, 1, 0, 0, 1, 14 by 3, 0, 0, minus 5 by 3, 1 and 8, and then you are having 2 by 3, 1, 0, 1/3, 0 and this is minus 2. So, the Zj minus Cj values, if you calculate 0, 0, 1/3, this is 0, this is 1. So, again if you see Zj minus Cj value is greater than equals 0 in this case for all j, Zj minus Cj is greater than equals 0 for all j, but the solution is infeasible, because two basic variable, namely x4 and x1, these are having the fractional part. Now, which is having the largest fractional part? For x4 it is 4 into 2 by 3, for x1 it is 2 by 3. Again for both cases fractional part is equals to 2 by 3. So, you can take any one. Say let us consider, we will take x1 as the for the constant we will take x1. So, for x1 what is happening then? If you take x1, then f10, f10 is, there is no integer part, this is f10. If you see this one x1, you will have f10, this is equals 2 by 3. Then this will not come, because this is integer, for corresponding to y1 no contribution, corresponding to y2 no contribution, corresponding to y3 there will be contribution, and that is f13, this is equals, the fractional part is 1 by 3. So, you can write down 2/3 minus 1/3 x3, this is equals, this is less than equals 0, or minus 1/3 x3 plus s2, this is equals minus 2 by 3. So, you see the problem. Initially I got one Grammarian slack variable, I got here some negative value, using dual simplex I am getting this, and again here I got the fractional part in the basic variable. So, I am repeating the process again. That means, now second time I am using the second Grammarian constraint for this, and the Grammarian constraint for this one is this one. So, there is S2 we are assuming. So, now what will happen? in this table you was having x 2, x 4, x 1, and with this one more basic variable will enter. The basic variable is S 2 and the corresponding equation is this one. So, let us see what happens. Our division variable, basic variables are then from the earlier one y 2, y 4, y 1 and S 2. Corresponding x values are x 2, x 4, x 1 and S 2. Your C j is 1 3 0 0 0, C b is 3 0 1 0. So, your B values, as I have told you, please note, for the first table these 3 rows will remain as it is. These 3 rows there will be no change. So, I am writing the 3 rows as it is, that is 1 0 1 0 0 1 and then 14 by 3 0 0 minus 5 by 3 1 and S 2 is 0, S 1 is not coming, the next one is 2/3, 1 0 1/3 0, S 2 is 0, and as I have told, for S 2 you will get from here. B value is minus 2 by 3. So, you take B by 2 as minus 2 by 3, coefficient of x 1 x 2 are 0, x 3 is minus 1/3. So, I am writing x 1 is 0, x 2 is 0, x 3 minus 1/3, x 4 is 0, S 2 is 1. So, coefficient of x 4 is 0, coefficient of S 2 is 1. So, you form the table like this, calculate the Z j minus C j values as usual. This is 1/3, 0 and 0. Again Z j minus C j greater than equals 0 if you see, but the solution is infeasible. So, there we will have only, since you are having one slack variable S 2 having the negative value. So, this will be going out. I am not telling how, because now you know using dual simplex method, and this will be your entering variable. So, the solution now your pivot element will be this. So, therefore, from the basis S 2 will depart and y 3 will enter. So, that you will now have y 2, y 4, y 1 and y 3. So, I am writing this y 2, y 4, y 1 and your y 3. Correspondingly, you are having x 2, x 4, x 1 and x 3. C j values are same 1 3 0 0 0. So, it is 3 0 1 and y 3 is 0, 3 0 1 0. So, I have to make this pivot element as 1 and correspondingly other elements in the other columns as other rows as 0. I am directly writing what is the result 1 0 1 0 0 0. Next one is 4 by 3 0 0 0 0 minus 5. This is 0 1 0 0 0 1, x 3 is 2 0 0 1 0 minus 3. Calculate the Z j minus C j value, Z j minus C j value, Z j minus C j for the first variable is 0, next one is 3 minus 3 0, 3 0 0. So, it is 0, next all 4 are 0. So, 0, this is 1. So, now if you see Z j minus C j greater than equals 0 and my decision variables are x 1 and x 2, and x 1 x 2 are having integer values in the basis. So, therefore, now we got the optimal solution, since Z j minus C j greater than equals 0 and the optimal solution is the and the values of the decision variables are integers. So, therefore, x 1 star equals 0, x 2 star this is equals 1 and your z max or z star if you calculate this is equals 3. So, once I wanted that I should get the integer values, in that case if you see integer values of the decision variables, my solution is x 1 star 0, x 2 star 1. So, that it is becoming z star equals 3. Whereas, if I take the decision variables can take any value, your profit is more, that is z star equals 4. But although the profit is less over here, as I told you the short problem which I will come next, I cannot take the values of the decision variables as fractions. So, therefore, I have to take the integer values also, although the profit is becoming the negative. So, I think the mechanism or the method is little bit clear how we are solving it. Just I will take one more example to solve for your illustration purpose. Just see this problem. The owner of a garment shop makes two type of shirts known as A shirt and B shirt. So, they are making two different type of shirts, A shirt and B shirt. He makes a profit of $1 and $4 per shirt on A shirt and B shirt respectively. He has two tailors X and Y for stitching the shirts. Tailor X and Y can devote at most 7 hours and 15 hours per day respectively. Okay? They cannot devote more than 7 hours, more than 15 hours per day. Both of these shirts are to be stitched by both the tailors, means both the tailors can stitch both type of shirts. Tailor X and tailor Y spend 2 hours and 5 hours respectively in stitching one's A type of shirt and 4 hours and 4 hours respectively in stitching one B type of shirts. That is, they take how many hours for stitching A type of shirt and B type of shirt are known to us. How many shirts of both types should be stitched in order to maximize the daily profit. We are talking daily basis. So, basically daily profit has to be maximized. So, how many type of this one should be made. So, this is the problem. So, what is I am taking two decision variables, x 1 is number of A type of shirt and x 2 is number of B type of shirt. So, what is your objective function? Objective function is maximize z equals what? What is the profit for A type of shirt is 1, profit for B type of shirt is rupees 4. I am making x 1 number of A type of shirts and x 2 number of x 2 number of B type of shirts. So, profit on A type of shirts will be 1 into x 1, profit on B type of shirt will be 4 into x 2. Therefore, my objective function will be z equals x 1 plus 4 x 2. I think the method is clear. Subject to what we are telling, to make his tailor X spends 2 hours of time and 4 hours of time for shirt A and shirt B respectively. That means, he takes 2 hours to stitch a shirt of type A and 4 hours to stitch a shirt of type B, and he can devote, tailor X can devote at max 7 hours in a day, because we are calculating this. So, he can stitch how many shirts in one day, 2 into x 1 and 4 into x 2 B type of shirts, and 2 x 1 plus 4 x 2 must be less than equal 7, because he cannot devote more than 7 hours. So, my first condition is 2 x 1 plus 4 x 2, this is less than equal 7. Similarly, for the other one, what is happening? It is taking, tailor Y is taking 5 hours to stitch A type of shirt and 4 hours to stitch a B type of shirt. So, how many shirts he is making? He is making 5 into x 1 plus 4 into x 2, and how much time he is devoting? That is 15 hours. So, therefore, the second constraint will be 5 x 1 plus 4 x 2, this must be less than equals 15. And obviously, number of shirts they are making. So, x 1 x 2 must be greater than equals 0, and both x 1 and x 2 must be integers from practical viewpoint. So, this was the problem. From the problem, we formulated the LPP. Now, once we have formulated the LPP, we are observing one thing, that the variables must be integer, it cannot take non-integer values. So, our first job is to write it in the optimized form. Again, you have to use two slack variables. So, x 1 plus 4 x 2 plus 0 into x 3 plus 0 into x 4, subject to 2 x 1 plus 4 x 2 plus x 3 plus 0 into x 4, this is equal 7, and 5 x 1 plus 4 x 2 plus 0 into x 3 plus x 4, this is equals 15 with the condition x 1, x 2, x 3, x 4 greater than equals 0 and x 1 and x 2 are integers only. So, from this we can formulate the table directly now. I am not showing this, I am directly writing the table, you have seen it, so that it will save some time. Here your basic variables will be x 3 and x 4 as we have done earlier. So, your basic variables are x 3 and x 4. So, it is here we are writing y 3 and y 4 will come. Here you are having x 3 and x 4. Your Cj values are, it was 1 4 0 0. So, I am writing from here 1 4 0 0. So, corresponding Cb value y 3 and y 4 are 0. Now, just write down the rows. B values are 7 and 15 over here. So, I am writing 7 and 15. Next, first row is 2 4 1 and 0, the coefficients. So, you are writing 2 4 1 and 0. For the second one 5 4 0 and 1. So, you are writing 5 4 0 and 1. Calculate Zj minus Cj, you will find minus 1 minus 4 0 and 0. So, this is the most negative. So, ratio you calculate 7 by 4 and 15 by 4 for this b by yj. So, the most minimum is 7 by 4, therefore, this one will be going out. So, therefore, x 3 will depart and x 2 will enter. So, in the next table you are having minus 4. So, this is your pivot element, means I have to make this element as 1 and correspondingly in this row this element as 0. So, here you are having y 2 and y 4. So, it is x 2 and x 4. These values will not change 1 4 0 0, Cb is 4, this is y 2 is 4, this is 0. Directly again I am writing, you can check it afterwards, 7 by 4, half, 1, 1 by 4 and 0, 8, 3, 0, minus 1 and 1. Calculate the Zj minus Cj value. Zj minus Cj is 2 minus 1. So, it is 1, 4 minus 4, 0, this is 1 minus 0, 1, this is 0, 0 minus 0. So, if you see here Zj minus Cj is greater than equals 0, but there is one variable whose value is fractional. There is one variable whose value is fractional, that is x 2. So, basically your x 2 is fractional over here. Since x 2 is fractional over here, therefore, from here you can x 2 is fractional. So, f 1 0 fractional value you can take, f 1 0 is 3 by 4, f 1 1 is half, f 1 3 is 1 by 4. So, f 1 1 is half, f 1 by 3 is equals to 1 by 4. So, the Gomorian constant, using Gomorian constant I am directly writing minus half x 1 minus 1 by 4 x 3 plus s 1, this is equals minus 3 by 4. So, one more variable will now enter into basis. Earlier there was y 2 and y 4, now you will have y 2, y 4 and s 1. So, correspondingly you are having x 2, x 4 and s 1. Cj values are known to you 1 4 0 0 0. So, s 1 as I have told from the earlier optimal table, first two rows will remain same. So, I am just writing 7 by 4, half, 1, 1 by 4, 0 and 0. This is 8, 3, 0, minus 1, 1, 0, minus 3 by 4, minus half, 0, minus 1 by 4, 0 and 1. If you calculate the Zj minus Cj values, that is 1, 0, 1, 0, 0. Zj minus Cj is greater than equals 0, but you have a negative number here S 1. So, use dual simplex method. So, departing vector will be this, entering vector will be this one. So, again, so now you will have y 2, y 4 and y 1. So, I am writing this y 2, y 4 and y 1. So, x 2, x 4 and x 1. Your Cj values 1, 4, 0, 0, 0. Your Cv values are 4, 0 and 1. So, this is 1, 7 by 2, 3 by 2, 0, 1, 0, 1, 1. This is 0, 0, half, 0 and 6. you can check it afterwards 1 0 half 0 minus 2, zj minus cj is 0 0 half 4 and 2. If you see zj minus cj values are greater than equals 0, but the solution is non-integer solutions, because x 1 is 3 by 2 or this is equals to half. So, you do not have this one. So, therefore, fractional part again x 4 and x 1 is again half for both. I am choosing x 4. So, once you are choosing x 4, that is f 20. So, I am writing, since I have used already this f 20, this is equals half and you will have only another fractional part on y 3, others are positive. So, f 23 equals half. You can formulate the less than equals inequality, then add Grammarian slack variable and you will get minus half x 3 plus s 2, this is equals minus half, and you formulate the next table. So, basically from here you are having y 2, y 4, y 1 and one more slack variable, sorry, this is s 2. This is S 1, this is S 2 will be added over here. So, now you are having y 2, y 4, y 1 and S 2. So, x 2, x 4, x 1 and S 2. Your C j is 1 4 0 0 0. So, C b will be 4 0 1 and 0. First two rows will remain unchanged 1 0 1 0 1 0. This will be first three rows 7 by 2 0 0 half 0, S 2 is 0. For the third one it is 3 by 2 1 0 half 0 and S 2 again is 0, and the fourth row will come from here. B value is minus half. So, you are writing minus half over here. X 1 x 2 coefficient is not there, x 3 is minus half, S 2 is 1. So, basically it will be 0 0 minus half 0 and 1. If you calculate zj minus cj, your zj minus cj will become 0 0 half 4 and 0. So, zj minus cj is greater than equals 0, but the solution is infeasible because you are having negative value in the basic variable. So, this will be the departing vector corresponding to this will be your entering vector over here. So, minus half will be the pivot element. Therefore, here you will have y 2, y 4, y 1 and y 3. So, I am making y 2, y 4, y 1 and y 3. Correspondingly, you are having x 2, x 4, x 1 and x 3. Basically, I will make this one, others are zeros. So, this will be 1 4 0 0 0. This is 4 0 1 0. I am directly again writing after modification 1 0 1 0 1 0 corresponding to x 4, 3 1 2 0 0 1. Next one is 1 1 0 0 0 and 1. The last one is 1 0 0 1 0 minus 2. If you calculate zj minus cj, this will be 0, next one is 0, next one is 0, this is 4, 4 is coming over here, and for the last one 0 0 1 is there. So, 1. So, if you see zj minus cj is greater than equals 0 for all j, and the values of the variables x 1 and x 2 are containing the integer values. So, the optimum solution over here is x 1 star equals 1, x 2 star equals 1, and if you calculate the z star value will be 5. So, like this way you are obtaining the integer values solution always whenever it is required. Here it may happen that your profit is slightly reduced if you would have taken the real values or integer values, but the solution is integer in the last problem as you have seen, where it is necessary that number of stars must be integer. So, this was Grammarian method. In the next class, we will discuss the branch and bound algorithm for solving the integer problem. Thank you.